Hello and welcome to another lecture, that is Pauli's exclusion principle. It is another quantum mechanical concept which determines how the electrons will occupy the electron states. So basically it determines the manner in which electron states uh, are filled with electrons. And so it stipulates that it stipulates that only two electrons occupy a electron state. So electron state or orbital can be occupied by only two electrons, and they have opposite spins. So for a particular orbital, let's say 2s. So this is a uh, one orbital. In a subshell, we have only one orbital. It has two electrons can be filled, and those two electrons will have opposite spins. Okay. And so based on this, we can say that how many electrons can each subshell have. Suppose, for example, when we take a subshell, it can accommodate two electrons. When we take p subshell, we know that p subshell has three orbitals. So 3 into 2, it can accommodate maximum of 6 electrons. And d subshell has 5 orbitals. So 5 into 2, 10 electrons. And F subshell has 7 orbitals, 7 to the 14 electrons can be accommodated in these subshells respectively. So, in an atom, there are different possible states for electrons to be filled, but all those possible states are not filled. The filling of these different states, it will be based on a particular uh, criteria or rule, that is lowest possible energy states are filled. So the filling happens, the electrons are accommodated based on the energy. So whichever the electron state has low energy, those electron states will be occupied in the hierarchy. So first the minimum lowest will be occupied. For example, if we take um, suppose if we take hydrogen. Suppose let's take a hydrogen atom. So we know that it has one electron. Okay, so where this one electron will be accommodated, it will be accommodated in the lowest energy state. And we know that the energy is like this. When we compare between principal quantum numbers, the first shell has lowest energy compared to 2, n equal to 2. This less than n equal to 3, less than n equal to 4. So here first shell has lowest energy. Then when we also know that in the shell there are subshells like SPDF. So uh, shell or orbital has each shell or orbit has subshells SP and DF. There also we know that S has lowest energy compared to P, which has lowest energy compared to D and F. So here we can say that this one electron will be accommodated in the lowest energy shell with lowest energy subshell. So the one electron of hydrogen will be accommodated in 1s. So this is the case. And if there are two electrons, those two electrons will be accommodated in this 1s. And we know that it has only one orbital, so two electrons will be accommodated in 1s. Now, when we take lithium, so lithium has three electrons. So first two electrons will be accommodated in 1s. Then it will see the next lowest possible energy. That is, after one is now over, it is done. There are no more electron states for accommodating the third electron. So it will go for two. So 1s2 is done, and next is 2, and 2 has in 2 we have S subshell as well as P subshell, and between S and P, which has lowest energy, S has lowest energy, so it will be 2s1. Same applies for all the other atoms. In this way, the electrons are filled. Uh, so basically, the configuration, the electronic configuration of any atom is based on the energy. Uh, Sometimes, like we have to see the energy of these shell as well as subshell collectively. Combinedly, we have to see. So that's how the electronic configuration is done for remaining atoms. So now, when the atom is occupied by electrons in this manner, it is said to be in ground state. So this is the ground state corresponding to lithium. When electrons accommodate based on this energy, that is from lowest energy states, when it is occupied, it is said to be ground state, and the ground state, uh, naturally this is in the ground state, the lithium atom. Now we can also excite the electrons in the lowest energy state to higher energies also, like uh, suppose by incidenting light we may also take this one electron in the 2s to, for example, 3s. It is also possible like this we can take, that is by excitation, that is by giving energy to this lithium atom we can excite. So when the electron goes to 3s, that is that particular orbital, 3s orbital, then we don't say that the atom is in ground state. Rather, now the atom is in excited state. So how we represent the electrons in an atom? Like for example, if we take sodium, we know that sodium has 11 electrons. So we have to represent how these electrons are present in the atom. So based on our representation, it should be understood that how the electrons are accommodated in the electron states. So it should be like, so it is like 1s 2. So first orbital is occupied by 2 electrons. So here we are representing the 1 is principal quantum number, S is azimuthal quantum number with the number of electrons. So this is done for first shell. Now in the second shell we have two subshells, that is 2s and 2p, and S subshell has only one orbital, so it can accommodate 2 electrons, whereas P subshell has 3 orbitals, so 6 electrons. And now 10 electrons are done, and in the third shell there will be 1 electron. So this is how we represent the how electrons are accommodated in um, different electron states. Now, whatever the electrons are present in the outermost shell, that is valence electrons. So here we can see that this 3s is this is the valence electron. Now there are particular atoms like you know, suppose when S and P subshells are completely filled, when these subshells are completely filled, then uh, we call that elements as noble elements. So these are noble elements, or basically these are gases, so we call noble gases. and they are not chemically reactive, they are stable. So for them, the outermost shell is completely filled. So if we take the examples like neon, argon, krypton. So here for neon it is 1s2, 2s2, 2p6. The outermost shell is completely filled. Therefore, there are no valence electrons here. So this is not chemically reactive. So how about the other elements that have um, valence electrons? For example, if we take aluminium, so how we have to calculate the number of valence electrons? Number of valence electrons we can calculate like this. So what is the electron? The atomic number is 13. So 13 electrons are present. We can replace 1s2, 2s2, 2p6, 3s2, 3p1. So the valence electrons are the ones that come after completely filled S and P, S and P subshells. So here, from here it is not completely filled. So we have 3s to 3p1. So three valence electrons in this case. So valence is calculated in this way, and for each atom, the valence number of valence electrons are very important in deciding its chemical and physical properties, and how it reacts with other atoms can be determined based on this valence number of valence electrons, and also with the so when these when these atoms which are not stable, they will react. So they will either react by sharing or by donating. For example, in case of donating, they become ions and react. For example, NaCl. In this case, Na will lose one electron and it forms Na plus. And here Cl will gain one electron and form Cl minus. And now these two react to form NaCl. And also there is another way of forming compounds by sharing the electrons. Suppose for example hydrogen we have, it has one electron. Now there is another hydrogen which has another electron. Now these two electrons are shared by both atoms and forms H2. So basically this is ionic compound, and this is covalent bonding. This is ionic bonding and this is covalent bonding. So this is the basis for forming uh, atomic or molecular aggregates based on atomic bonding. So this is all about the Pauli's exclusion principle and valence electrons and bonding in between atoms. Thank you so much for watching this video, and please subscribe to get more videos.